All right, in the last video, we talked about a sound source that was actually moving towards us or away from us. And we derived two equations for if it was coming towards us or away from us. In this video, we would like to derive an equation for a sound source that is not moving, but we're actually running towards it or we're running away from it. And we want to figure out what equations would we use, Doppler effect equations would we use in that situation. So again, I'm going to, I'll draw a little sound source here, okay? And then I'm going to look at waves. Let's say that there's waves, coming out here, and then here's another one right here, and I could keep going and so on, okay? And let's say that there's a person. There's a person that is that's right here listening to this wave. This wave is just hitting this person right there. Okay. Now this is a stationary sound source, so this source right here is not going to be moving, and so it's just going to have nice interval waves here. The problem is that this person here is going to be running this way, so they're going to actually come in contact with these waves that are being emitted at a faster rate than they normally would be. So again, it'll be a higher frequency, and they will hear a higher frequency sound because they're coming into contact with these waves faster. So it's a little bit different than the other situation we did in the last video. Okay, so this person is running this way now. So let's imagine. So what we have here is we have the actual, from here to here. We have the actual wavelength, okay? There's the actual wavelength. And this person, though, is going to run over, as this wave continues to move forward, this person is going to run this way towards that wave. So when this wave right here, when this wave here gets to be like right over here, we'll say, I'll put it right in there, okay? Now this person is actually right there. So instead of waiting for this wave to get all the way over there, this person has run up to meet this wave coming this way, and he's met him right there, okay? So really then for this person, the wavelength seems like it's from, this crest, which you just had, to the next crest, which would be right here. So the wavelength, again, seems shorter than it would normally would be. So right here, so what we have really technically is from here's the next wave that's coming, and here's that wave that's going to be there. So in between here and here, we have this this observed wavelength, because the wave started here and then it got to here, and so now that's the distance between those. So in between here we have the observed wavelength, and then right here we have remember we have velocity equals d divided by t, so we have d equals v times t. And this v right here is the velocity of the observer, right? It's the observer that's actually listening to the sound is the one that's moving. So that's the velocity of the observer. What is this t? How much time does it take from him to get right from here to this next wave? Well, actually, that is the amount of time it would take between one crest and the next crest. That's the period of the observed wave. It's the period of the observed wave. Okay, so this right in here, this distance in here would be VO, the velocity of the observer, times the period of the new wavelength, So we can start our derivation here again. We can do the observed wavelength. The observed wavelength should equal the overall wavelength, right? Minus the velocity of the observer times the period of the observer. Now, if you remember again, the velocity equals frequency times wavelength, right? So wavelength equals velocity divided by frequency. It would also equal the effective wavelength would equal the velocity divided by the effective frequency also. Okay, so in for this new observed wavelength, I could put v over the new observed frequency. In for the actual wavelength, I could put the velocity over the frequency. And then minus VO, and what is the observed period? Well, the observed period would be an inverse of the observed frequency, so I could put VO over the observed frequency. I could leave V over F equals, I could take this thing to the other side, but I'm going to put it over here, so it'd be V FO plus VO over FO. And then I'd have V over F would equal V plus VO over FO. And then I could flip the whole thing. So I'd have F over V equals FO over V plus VO. And I could solve for the FO. So I'd have FO would equal F times V plus VO all over the V. Okay, and so this would be find the frequency, the observed frequency would equal the actual frequency, right? The observed frequency would equal the actual frequency times this ratio. And this ratio is the velocity of the sound, speed of sound, plus the velocity of the observer, how fast it's moving into the sound, divided by the velocity. So if the velocity, if the observer moves faster, then this number up here is going to be even bigger, right? And you're going to get a higher frequency. So this right here is away. And again, if you went all the way back up here and put a plus sign in there instead to figure out what would happen if you had waves going this way, but there was a person here and they were running that way, right? Running this way. They'd be running with the waves coming at them, so it would make the wavelength even longer, right? Or a lower frequency. So that equation then the frequency of the observer would be the frequency times V minus VO over V. This would be towards. This would be towards. In that situation. Whoops. I did that backwards, so it's terrible. So yeah, so this whole first part here, this first equation here, was the person running towards, right? Person running towards, and then what we just did there was running away. Okay, so the plus version here is towards, and the away version is a minus on this. But in all of our equations, just regular old V is going to be the speed of sound. The speed of sound. In these equations here, we had VO. That was the velocity of the observer that's listening to the sound. In the last video, we had a VS. That was not the velocity of the sound. That was the velocity of the source of the sound. That's going to be kind of confusing. In the next video, we're going to show you that you don't have to memorize 4 different equations for all 4 different situations. You can memorize one equation, or you don't have to memorize it. You have it on your notes. You can use one equation for any situation that's given to you, or even if maybe we have this sound source running towards you and you're actually running towards it. So now you're going to have a really high frequency, right? How do I figure out what that frequency would be if they're both moving? So I'd have to use 2 of these equations at the same time, and we can show you how you can easily do that.